Welcome to AI Codecast. We love breaking down tricky coding problems, and today we're going to be diving into the world of palindrome pairs.
Oh yeah, palindrome pairs.
We have a list of words,
Right.
and you need to find all the pairs that create a palindrome when they're combined.
It's a classic problem, really gets you thinking about strings and algorithms.
Yeah, so like bat and tab would be a matched nail that formed a tab.
Exactly.
But the challenge is to find all of the pairs.
Right. And doing it efficiently.
Especially if you have a massive list.
Tons of words.
It's like trying to find two puzzle pieces.
Yeah.
In a huge jumbled box that fit perfectly together.
Perfect analogy. And like solving a puzzle, we have different approaches we can take to solve this problem.
Okay, cool.
Let's start with the most simple one, brute force.
Okay, brute force. We always start with brute force. What does that look like for this problem?
So imagine you're checking every single pair of words one by one
Okay.
to see if they form a palindrome.
Okay.
You pick a word, compare it with every other word in the list.
Yeah.
Combine them, and then check if the result is a palindrome.
Sounds simple enough. I bet it's not the most elegant solution, though.
You're absolutely right.
Especially if our word list is really, really big.
Yeah, it gets really time-consuming as the list grows.
Right.
Like in the worst case, you're comparing every word to every other word.
So if we have like 1,000 words, we could end up doing 1,000,000 comparisons.
Exactly.
Right.
And that's why we say the time complexity is big O of n squared k,
N squared K.
where n is the number of words and k is the average length of a word.
I'm starting to see why we need something a little bit smarter
Yeah.
than brute force when we have lots of words.
A lot of words especially.
Can you explain a little bit more about the time complexity there?
Yeah.
What makes it n squared K?
So the n squared part comes from the fact that we're comparing every word to every other word,
All right.
which gives us n times n comparisons.
Okay.
The t comes from the fact that for each comparison, we also need to combine the words and check if it's a palindrome,
Right.
which means we have to go letter by letter
Right.
in the word.
So we're not just doing the comparison.
Right.
We're doing extra work.
We're doing extra work for every comparison,
Okay.
which adds to the cost.
Got it.
And this can become a really big bottleneck when we have tons of words.
Okay, so we've established that brute force, while easy to understand,
Yeah.
not the way to go.
Not really.
What if we could organize our words in a smarter way so that it speeds up the search?
That's a great question.
Yeah.
That leads us to more sophisticated approaches.
Okay.
One tool we can use is a hash table.
A hash table.
A hash table.
Okay, now that sounds interesting. I'm picturing like a table with buckets, and each bucket has a jumbled mess of words.
Not quite, although it's a fun image.
Right.
Think of a hash table more like a well-organized library.
Okay.
Instead of going through every book on every shelf, you have a chord catalog. That tells you exactly where to find a specific book based on the title.
I gotcha. So instead of comparing the words directly, we're creating a system that lets us quickly look up potential matches.
Exactly.
Okay, cool.
In this case, we can use the hash table to store each word along with its index in the list.
Okay. I'm starting to see how that might be useful.
Yeah.
But how exactly does this help us find palindromes?
Oh.
Are we just throwing words in there and crossing our fingers?
Not quite.
Okay.
Remember, the key is to understand how palindromes can be formed. Let's break down the possible scenarios.
Okay, let's unpack those palindrome possibilities.
The first case, the simplest case, is when two words are the exact reverse of each other,
Okay.
like dog and God.
Right.
With a hash table, we can just quickly check if the reverse of a word exists in our word list.
So we take a word, reverse it, and see if that reverse word is in our hash table.
Exactly.
If it is, boom, we found a pair.
We found a pair.
Simple, elegant.
Now let's move to a slightly more complex scenario.
All right.
Imagine one word has a palindromic suffix, and the other word is the reverse of the remaining prefix.
Okay.
So, for example, ban and anana.
Okay, so anana is a palindrome on its own,
Yes,
and ban is the reverse of the remaining letters, nab.
exactly.
Interesting.
So in this case, we need to check each suffix of a word to see if it's a palindrome. If it is, we reverse the remaining prefix and see if that exists in our hash table.
So we're breaking down the word strategically
Yes.
and using the hash table to quickly rule out possibilities.
Exactly.
What's the third scenario?
It's basically the mirror image of the second one.
Okay.
We check if the word has a palindromic prefix.
Uh-huh.
If it does, we reverse the remaining suffix and look for that in our hash table.
So like in our ban-ana example, we would check anana
Yeah.
for a palindromic prefix ana.
Yes.
Reverse the suffix na and look for it in the hash table.
Gotcha.
Got it.
By checking these 3 cases, we can cover all the ways 2 words can combine to form a palindrome.
This is starting to feel a lot more efficient
Yeah,
than our brute force approach.
a lot more efficient.
We're not just blindly comparing every single we're using the structure of the palindromes themselves
Yes.
to our advantage.
To our advantage, exactly. And the beauty is hash tables are really fast.
Right.
So we can do lookups really quickly.
So how much faster are we talking here?
So the hash table approach brings our time complexity down to big O of n times k squared,
Okay.
which is a significant improvement over n squared k.
Okay.
Especially when k is much smaller than n.
Okay, I'm trying to wrap my head around this. Can you give us a real-world scenario
Sure.
to illustrate that?
Imagine you're trying to find a specific spice
Okay.
in a spice shop, a well-stocked spice shop.
Okay.
Brute force would be like sniffing every single jar
Oh, yeah.
until you find the one you're looking for.
That sounds tedious.
Very tedious.
Yeah.
But with a hash table, it's like having a spice index.
Okay.
It tells you exactly which shelf and jar to go to.
Much better.
Much better.
Yeah.
You find your spice in a fraction of the time.
I like that analogy.
Yeah.
Okay, so you mentioned that there's another data structure we can use.
Yes.
I think you called it a trie.
A trie.
A trie.
Yeah.
Okay, so I'm picturing a tree with words branching out like all over the place.
Yeah, it's a tree-like structure.
It is.
It's really well suited for working with strings.
Okay.
And in this case, it can be even more efficient than a hash table.
Interesting. Okay, so how does a word tree help us find palindromes?
Imagine each node in the tree represents a letter.
Okay.
We build this tree, trie, by inserting the reversed version of each word.
The reversed verse.
The reversed version.
Okay, why do we have to flip them?
So this is the key to efficiently searching for those palindromes.
Okay.
Because it lets us check all 3 of our palindromic scenarios in one go.
Okay, I'm ready. Walk me through how this trie traversal works.
Okay, let's take the word banana.
Okay.
We reverse it to get ananab,
Okay.
and we start traversing the trie letter by letter. As we move, we check if the current portion is a palindrome.
So with ananob, the first A is a palindrome, then Anna, then Anna.
Yeah, exactly.
Okay.
Now let's say we've traversed Anna, which is a palindrome.
Right.
At this point, we check if there's a word stored at that node.
Okay.
This means the reverse of that word is a suffix of our original word, banana.
So if there is a word there at that Anna node,
Yes.
we found a potential palindrome pair.
We found a potential pair.
It's like we're walking down this path,
Hmm.
checking for palindromes along the way,
Yeah.
and seeing if there's a match waiting for us at the end.
Exactly. And we do this all the way to the end of ananab.
Okay.
And if we hit a node where the remaining letters form a palindrome,
Uh-huh.
and there's a word stored there,
Yeah.
we found another match.
So it's like each branch of the trie is a path
Yeah.
of a potential palindrome pair.
Exactly.
Very cool.
Yeah.
Very elegant.
And it's really efficient,
Yeah.
especially for large data sets.
Uh-huh.
The time complexity is dominated by building and searching the tries, which is O of k squared n.
Okay.
However, the trie can become very large, so the space complexity can be a problem.
So there's a trade-off. We gain speed, but we might need more memory.
Exactly. It's like having a massive library
Okay.
with an amazing card catalog.
Right.
The catalog makes it easy to find books, but it takes up a ton of space.
So choosing between the hash table and the trie depends on what we're working with.
Exactly. If memory is a big concern,
Yeah.
a hash table might be better.
Okay.
But if we need speed and we have lots of data, then a trie usually wins.
It's like choosing the right tool for the job.
Exactly.
Yeah, sometimes you need a hammer, sometimes you need a scalpel.
Right.
But before we wrap up, you mentioned online algorithms earlier.
Yes.
What exactly are those? Is that like code that writes itself?
Not quite yet.
Okay.
They're designed to handle data that's constantly coming in,
Okay.
rather than having all the data up front.
So instead of getting a big list of words,
Yeah.
we're getting them one by one,
One by one.
like a live feed.
Like a live feed, think about building a palindrome detector that works in real time
Oh,
as words come in.
That sounds like a whole other level of complexity.
Yeah.
Do our hash tables and tries hold up in that world?
So the hash table approach,
Uh-huh.
while great offline,
Yeah.
struggles in that scenario.
Okay.
It needs to have all the words up front to build that efficient lookup table.
So it's like trying to use a spice index
Yes,
that's constantly outdated as new spices are being added.
exactly. We're always
Yeah.
either playing catch up.
Gotcha.
But the trie, with a little modification,
Okay.
can handle this online challenge.
Okay.
We actually need 2 tries.
2 tries.
One for words in their original form,
Uh-huh.
and another one for the reversed words.
Why do we need 2?
So the trie with the words in their original form lets us find pairs
Okay.
where the new word is the second word of the pair.
Okay.
And the try with the reversed words lets us find pairs where the new word is the first word.
Ah, so we're covering both ends of the palindrome as the words stream in.
Exactly. This dual try approach makes sure we can efficiently find those palindromes
Okay.
no matter where the new word goes.
That's really clever.
Yeah.
So we've gone from brute force, which is like wandering aimlessly through a spice shop, to this elegant system with 2 tries,
Yeah.
which is like having a team of expert spice guys.
A perfect analogy. It shows how important it is to understand not just the algorithms, but also how well they do under different conditions.
Yeah, it really shows you got to pick the right approach for the problem.
Exactly.
So as we wrap up our deep dive into palindrome pairs,
Yeah.
what are some of the key takeaways for our listeners?
I would say, first, really take your time to understand the problem.
Right.
Don't just jump into coding. Think about those palindromes.
Yeah.
Think about the different ways they can be made.
Yeah, like lay out the puzzle pieces before you try and force them together.
Exactly. And then explore those different approaches. We've seen brute force.
Right.
We've seen hash tables. We've seen tries.
Right.
They all have pros and cons.
Yeah.
So picking the right one depends on, how much data you got, how much time you got, memory limits.
It's like a toolkit.
It is.
Full of different tools.
Yeah.
Got to pick the right one.
Exactly. And then finally, don't be afraid to push beyond the basics,
Yeah.
We talked about online algorithms.
Right.
That opens up a whole new world of problems.
Right, like solving a puzzle and the pieces keep getting revealed one by one.
Exactly.
You got to change your approach.
You got to adapt.
Yeah.
And that's what makes coding so cool.
Right.
There are always new challenges to tackle.
New approaches.
New ways to do things.
Yeah.
New levels of efficiency to reach for.
Absolutely.
Yeah.
So for our listeners who are eager to put all this into practice,
Yeah.
any final words of advice?
Experiment,
Yeah.
Try these approaches out.
Uh-huh.
Play around with them. See if you can come up with your own optimizations. That LeetCode Playground link we mentioned is a great resource.
Absolutely nothing beats getting your hands dirty with some real code.
For sure.
Awesome. Well, huge thanks to our expert for breaking down palindrome pairs.
You got it.
And to all our listeners out there, keep coding, keep learning,
Keep learning.
and keep those deep dives going. We'll catch you on the next episode of AI Codecast.